Hello, Mr. Claudia here. Today we're going to be continuing our exploration of logarithms by looking at log laws. We've learned a whole bunch of exponent laws, and since we know logarithms are so entwined with the story of exponents, there must be some similar laws that apply to logarithms. So you're actually going to discover these yourself. Fun little activity here. Basically, you're going to use your calculator and just solve each of these really quickly. So log 2 plus log 3. So log 2, remember that's a number. It's base 10. There's no base, so we know it's base 10. Plus log 3. Make sure you're careful with order of operations in your calculator. And I get 7.778. Remember, about 3 significant figures. And just write the numbers in there. I'll let you do this on your own and try to look for patterns. So you could pause the video now and work through this fun activity on your own. We'll see you in a minute. Welcome back. After doing that fun activity, hopefully you've noticed some patterns. The first pattern, well, the pattern is that the questions are always the same. The numbers that you get, the final answers, are always the same for any given pair. So that means that log 2 plus log 3 is the same as log 6. What's the relationship between 2, 3 to get 6, 3 and 7 to get 21, 4 and 20 to get 8? Well, it seems like log 6, I've basically taken the 2 and 3 and multiplied them together. So that's my first log law. If you have log A base C plus log B base C, so if you have two logs with the same base, then you can actually just rewrite this as the product of those two arguments, a, b. Similar, if you have these two are the same, so if you're subtracting logs, you can actually just divide the argument. 6 divided by 2 gives you 3, 12 divided by 3 gives you 4, etc. So this is log A base C minus log B base C. This is going to be log A divided by B base C. And finally, we notice that these pairs are the same. So how do I go from, how are these similar? Well, this is the same except I have 2 to the power of 3, so this becomes an exponent. 5 to the power of 2, 3 to the power of negative 4. So we have this last log law. If you have a constant multiplied by a log, you can rewrite the log as same base, but that argument raised to the constant. Now it's hard when you look at these in so many letters. It is a little confusing to look at this. But as we found with the exponent laws, once we start practicing, it'll hopefully make a bit more sense. So we'll start practicing. Actually, what I usually like to do is, you shouldn't just take my word for it. You should probably say, I want to see some proof. So I'm just going to write the proof here. The proof will never be tested. I'll never ask you to show me this. But this is more just to show you that mathematically, this logic is sound. We just did some tests with the calculator, but the proof is what really confirms it. So if you have x is equal to a to the m, and if you have y is equal to a to the n, then I can rewrite these as logarithms. So it's going to be log base a of x is equal to m, and log base a of y is equal to n. So I just rewrote it using the definition of a logarithm. We know that x times y is equal to a to the power of n times a to the power of n. I just took these and subbed them in. But I know I can solve this using my exponent laws. So this is where I add my exponents. Now, if I were to log both sides of that equation, I get log, let's say log base a of xy, and log base a of a to the m plus n. Well, look at this, log base a and raised to the power of a. These two things undo each other, so I'm left with m plus n is equal to log a xy. And I know what m is, it's log x, and n is log y. So I can rewrite this There we go. So that's my proof. Again, you're never going to have to need to memorize this or show this again. This is just for your information. Okay, let's start doing something practical. Let's start actually solving some questions. So if I want to know what log 5 plus log 3 is, or express them as a single logarithm, I can do that, because if I'm adding two logs that have the same base, so in this case the base is 10, I just multiply the arguments. So this is going to be log 5 times 3, or log 15. Don't have to show that step, but this is just our first time. If I have logs with the same base being subtracted, well, look at this. I can just divide 24 divided by 8. So that gives me log 3 base 3, which hopefully you remember is 1. It's a special case. Okay, what about this one here? Log 5 base 2. Ooh, I can't subtract these because there's no rule that allows me to subtract logs with non-logs. However, if you remember from that last question, I know 1 is equal to log of 2 base 2. These are equivalent things, because log, where the argument and the base are the same, is always 1. Now I can do that trick. I can do log base 2, 5 divided by 2. And that's a valid answer like that. Okay, let's try using that third example. Here we have, if I have log with a constant in front, I can bring that exponent up into the argument. So this ln 7 times 2, this becomes ln 7 squared. And this 3 ln 2 becomes ln 2 cubed. This isn't magic, like this is something we investigated, and again, there's a similar proof, just like I did here. There's a similar proof out there. You can go Google it right now. That would show that this is true. So I'm not making up math, I'm using a law. Now that I have a subtraction, well, let me just clean this up. This is ln 49 minus ln 2 times 2 is 8. And when I'm subtracting logs, now I can just divide these. There we go. Note the brackets are not really necessary. Like I could write this as just 49 over 8. The brackets are implied, so whatever is after the ln is the argument. Same with here, the 7 squared is not really necessary. If I left out the brackets, it would just be ln 7 squared, and you're assuming that whatever immediately follows ln is the argument. Okay, this next question, okay, let me try to turn this into 3 squared, like that. And remember, there's an unwritten base 10 here. So now we can do the same thing we did before. This is going to be plus 3 log 10. So remember, there's the unwritten base 10. Now, I can't yet do anything because I have this constant here, but I can get rid of this constant by moving it up. And again, this log 10 base 10 is just 1, so this is 3 times 1. But now, because of my log laws, I'm not making up any math when I do this. And before I multiply these numbers together, I can clean them up. This is log base 10, 9, plus log base 10, 1,000. Now, when two logs with the same base are being added together, you can just multiply the arguments. So this is log base 10, 9,000. And this is my favorite one, log 8 divided by log 4. So a lot of students say over here, oh, well, log 8 divided by log 4. Well, that's log 2. Because 8 divided by 4 is 2. This is most certainly not correct. You just made up math. Go back to the rule. The law is if I have a subtraction of logs with the same base, I can then divide the arguments. This is not a subtraction of logs. This is a division of logs. So you can't use this. This is a made-up rule that you're using here. The only way you could solve this, and it's kind of ugly, is log 8 you could split up into 2 times 4 over log 4. And now the 2 times 4, you could then separate that into an addition of logs, so you could go backwards. And now technically this is log 2 over log 4 plus log 4 over log 4. So that gives you log 2 over log 4 plus 1, because these divide out into each other. I don't think that's really similar, but that's really the only manipulation I can do. You could pretty much have left it like this. You cannot do this. So please be very careful. These are confusing, the log laws. Even though there's only 3 of them, it's very confusing. There's a real tendency to make up math. So I'm just looking at my page. I have another solution for this question that I've developed over the years, which is log 8 over log 4. This is log 2 to the power of 3 over log 2 squared. If I bring the exponents down, which is one of my log rules, then the log 2's cancel out and I'm left with the answer 3 over 2. Now there's a nice answer. But as you'll notice, I wasn't able to do, just be very careful about this bad solution over there. Okay, let's turn the page and continue. Okay, let's practice some more of these laws. What I'd recommend is to pause the video now and try doing it yourself. These are almost ripped from the headline IB exam questions. So try it yourself and then you can come back and look at the answers. Okay, welcome back. So here I see that the logs, they have the same base, so I can multiply my arguments. So I have log base 2 x times 4x. So that gives me log base 2. Now x times x is x squared, so 4x squared. Again, you could put the brackets there if you wanted around the argument, but they're not necessary. It's implied. Okay, here, whoa, I've got lots going on here. Single logarithm. Let's try doing just the first 2 first. So they have the same base, so I can then divide. So I end up with 8x cubed over x squared plus log base 2 y over x. Now, well, I might as well simplify this a little bit. Log base 2 8x plus log base 2 y over x. Now I am allowed to multiply the exponents, or the arguments. So I end up with 8x and y over x. Now, again, this is implied that this is the argument. It's getting a little confusing though. I'm just going to put a square bracket there to show me that this is all inside the argument. When I do this multiplication, the x's cancel out, so I'm left with log base 2 of 8 and y. And the next question. So, oh, I'm very excited. I can divide the arguments, but wait, I have these coefficients in front. My laws don't work if there's coefficients in front. So I have to get rid of the coefficients by using that third log law. Let's write this one as, I'm going to write as y to the negative 4, because this is just y to the negative 1. And then this is going to be log 2xy cubed. So the 2 goes up here, I get x squared. The 4 goes up here, I get y to the negative 4. The 3 goes up here, but it goes to the entire argument, xy. So I have this situation where the cubed has to be applied to the x and the y. So let me just write one more line. Log base 2 x squared minus log base 2 y to the negative 4 minus log base 2 x cubed y cubed. Now, do you think we're ready to do this all in one step? Sure, log base 2. I have x squared in my numerator, divided by y to the negative 4, divided by x cubed, divided by y cubed. That's very messy, but I should be able to figure this out. Log base 2. So I have x over x. I have too many x's on. I have one x on the denominator. And actually, let's do this first. So let's do x squared. The y to the negative 4 is going to come to the numerator. Then I have x cubed and I have y cubed. That's a little bit easier. Now I end up with log base 2, 1y on the top and 1x on the bottom. Okay, and again, this is a classic IB style question. They tell you what log x is and what log y is. Can you solve this question now? So let's try doing substitution. Okay, log x. I don't have log x. I have log x cubed and log y squared. But I can't sub this into this. Resist the temptation to make up math here. Can I cube this and cube this to get x cubed? Well, no, that's not a rule we've learned. This is a logarithm we're dealing with. A log doesn't let us do that. I only have 3 log laws. Remember, there they are right there. So the only thing I can hope to do is maybe split up these. So let's try doing that. So if I split these up, I'm going to have log x cubed plus log a y squared. Because they're multiplied in the argument, I'm doing the opposite of my log law. This is splitting them apart. But I still can't do direct substitution because I have log x and this is log x squared. But we have another log law where I can bring that coefficient down, or that exponent down. Oops, sorry, it's gone. And I can bring this exponent down. Now life is good. Now I can do a direct substitution. Log ax, log ax. So now I know that this is 3 times 0.2 and this is 2 times 0.5. So that gives me 0.6 plus 1, so I get the answer 1.6. So that's what I did. I brought that 3 down, I brought that 2 down, and now look, that thing that I was given is right in my question. This next question, a similar problem. How can I split up the x and the y? They're so intertwined. I mean, there's even a square root. Actually, the square root bothers me the most. Let's start by writing this out without a square root, but with a rational exponent. Okay, now things are starting to make a bit more sense. This division I can split up into subtraction, but first I have to get rid of the half. So I'm going to bring the half down. Now, this log gets split up. So let's split it up. Again, you can imagine that this whole thing is in a bracket. So now I have log a x minus log base a y to the power 4. So the log x has been freed, but I still have to worry about this log y. Well, I can bring the 4 down. Now I have log x and log y. Now I can do my direct substitution. So I have 0.2 minus 4 times 0.5. That gives me half. 0.2 minus 2. Running out of space here. That gives me half of negative 1.8, which gives me negative 0.9. Okay, phew. So log laws, there you go. Your homework for today is top of page 124, number 1 to 3, bottom of page 124, number 1 to 6, page 126, number 1 to 3 and 5, and there is a solution in the error. There's an error in the solution. Page 124, number 2 BC, so just beware. Now, you'll notice there's a section at the bottom of the page. I don't have any other time where I can really squeeze in change of base law. So maybe go for a stretch, pause the video, then come back and let's look at the change of base law, which is this kind of fourth law that has a very specific application. So go for a quick jog, and I'll see you in a minute. Okay, welcome back. We're going to just look at this change of base law. It's a little tiny kind of extra lesson that goes in with this section. The change of base law, let me write the change of base law just in big letters here. If I have log of A base B, I can rewrite that as log of A base C over log of B base C. So that's the change of base. All of these laws, by the way, are on your IB formula sheet, so don't worry too much about memorizing them. Can I show you the proof? Again, I'll never ask you to reproduce the proof, and I don't need you to memorize this or anything. Just want to include it for understanding. So if you have x is equal to log A base B, then you can rewrite this as A equals B to the x. That's just my definition of a logarithm. If I log both sides, I have, again, I'm going to log this both sides. So I'm going to log A base C, and I'm going to log B to the x base C. So I chose some arbitrary base C. It could be anything, just different. But it has to be the same, because whatever you do to one side, you do to the other. Now I can use my log law. So I have log A base C is equal to x log B base C. So when I solve for x, I end up with log A base C over log B base C. That's our proof. Okay, don't worry too much about the proof. Worry about this confusing law. If I have a log of a number, base some other number, I can split it up into a division with using some third arbitrary base. This could be any base I like, base 10, base E, base 1000. We teach this to students for a really specific reason. If you're in a non-IB class, I teach this to you so you can solve difficult logs. For example, look at this one, log 9 base 4. On my calculator I have in a regular grade 12 class, I can only do log base 10, right? Log 9 base 10. I can't solve log 9 base 4. However, with the change of base formula, I can, because you rewrite a log with respect to a third base of your choosing. So I'm going to rewrite this using log 10, obviously, because that's the one that's in my calculator. So log base 10, 9, over log base 10, 4. You can choose any base you like. But they must be the same. Base 10 is best. It is in the calculator. So now I've rewritten, so I took the argument, right? So the A base 10, and then over the base, so log 4 base 10. And now I can type this into my calculator. Log 9 divided by log 4. And that gives me approximately 1.58. So the reason we teach change of base in a regular grade 12 program is just so you can solve these types of logs. Doesn't have too much extra purpose, and it's a very predictable kind of question you would get. In IB, they like to mess with you a bit more. They, especially in the question, they would traditionally use this change of base formula in a non-calculator test. Because remember, our IB calculator can solve this question without even having to use the change of base formula. I would just press log base 4 9. It's so powerful, it gives me the answer right away. So they would never give you a question with change of base law on a calculator exam, but on a non-calculator exam they might. Here they've given you log 7 and they've given you log 9, and they want you to find log 9 base 7. And I mean, this is a confusing question, but look at the problem here. This should be the red herring. The bases aren't the same. How can I rewrite this in terms of these if this is base 4 and this is base 7? Look at my other questions. I was always dealing with base A, base A, base A, base A, base A. Here the bases are different. So the logical solution is I have to change the base. The change of base formula is on your formula sheet. But remember, it's just log of the base, or of the argument, over log of the base, and I have to 7, sorry, it shouldn't be 4, it should be a 7. And I have to choose some arbitrary third base. Well, I'm going to choose 4 because that's what I've been given in my question. As long as they're the same base, it's fine. Now I can just do direct substitution. Log 9 base 4 is Q, and log 7 base 4 is P. There we go, all done. So I think there are a few questions in that homework about change of base. I hope they are. This is a kind of an extra thing to worry about. Like I said, there's 2 reasons we teach it. Hopefully you enjoy yourself with that homework, and I will see you next time.